Hi, my name is David, and today I'm going to be talking about Coulomb's law. So, Coulomb's law, as you can guess, was made by a man by the name of Charles Augustin de Coulomb, who was a French physicist who lived towards the end of the 17th century and early 18th century. His law mainly explains the relationship between two objects that have a charge on them and the distance between them, and how those variables, along with his constant, will give you a force in newtons. So first off, we're going to look at his formula. So as you can see here, Coulomb's law is in order to solve for force is equal to K times the product of Q1 and Q2 over R squared. And as you'll see just under it, F is the electric force or the electrostatic force, and K is Coulomb's constant, which I'll talk about in just a second. Q1 and Q2 are the charges of the objects that we're looking at, and R is the distance of separation. I know in other equations R stands for the radius. That's not the case here. It's just the distance, so it could be D. And as you look at the relationship, Q1 and Q2, we're looking at the absolute value of that product, because if Q1 were positive and Q2 were negative, meaning opposing charges, we know the resulting force would be attractive. The two objects would attract to each other. But if Q1 and Q2 had the same sign, they were both positive or both negative, that force would be repulsive. And this law is mainly there to show us what the magnitude of the force would be, whether it be attractive or repulsive. As you can see, the distance, R, is squared. So as the distance increases, the force exponentially decreases. And with Q1 or Q2, they have the same input into the final result. So whether K1 is very large or K2 is very large, both will have a positive impact on the force, meaning as they increase, so will the force. And so as I said, Coulomb's constant its value is 8.99 times 10 to the 9th, and it's measured in newtons times meters squared over Coulomb squared. And its main purpose in this equation is to make it so that meters and coulombs will cancel out, so that force, as we know, is measured in newtons, and that will be the only unit left over. So as we can see, if you multiply two charges, Q1 and Q2, you'll get coulombs squared, since the charges are measured in coulombs. And if you square the distance in meters, you'll get meters squared. So in the final product, you get Coulomb squared over meter squared. But conveniently, in Coulomb's constant, it's meter squared over Coulomb squared, and those two units will cancel out, leaving us with force in newtons. And so as I have here, I have a balloon, well, two balloons. And these balloons right now don't have a charge. But if I were to, say, rub them against my hair or rub them against my clothes, the electrons from my clothes or my hair will rub on to the balloon, giving it a negative charge. And as we see with electrostatic force, it can sometimes be compared or related to magnetism, because we see magnetism, we know that poles attract, like poles repel, and different opposite poles attract to each other, which is the same thing with charges. We just can't see, they're not labeled. We won't be able to see what the charge is, but we know that the electrons move from my hair or my shirt, my sweater, to the balloon. So just to show how this force really does exist, I'm going to tilt the camera just a bit so you can see the paper here. And I'm going to just spill some salt on here. And you may not see it, but you can sure hear it. And as I hover this balloon over the salt, nothing happens, because there's no force acting on there. The balloon doesn't have a charge on it. But if I, like I said, rub it against my sweater to pull off some electrons, giving it a net negative charge, now this balloon does have a charge, and will be able to exert a force with the salts. And as you may be able to mostly hear, I would say, and maybe you'll be able to see it, you can see that the balloon does in fact draw the salt. And obviously we know balloons aren't magnetic, and this this force is not gravity, it's electrostatic force, electric force. And just to show, as we still have some salt crumbs there, this balloon that hasn't been measured with, again, will not pick up any salt. And so, as we see there, this force can be used. As I said, if I were to rub this balloon that didn't have a net negative charge, and then I'd have to re-rub this balloon since it might have lost its charge by then. If I were, this experiment would not, you can't really see it, but as you pull the balloons closer to each other, they have a repulsive force. And I mean, I can't even really feel it. It's very, very small, but they are repelling each other because they have the same charge, both negatively charged. And as they get closer together, that force increases and you'll be able to feel it. Obviously, this force in newtons would be very small. Like I said, I wouldn't be able to feel it very well. And as I kind of looked over the internet as what this charge on the balloons could be, someone suggested that it could be around 10 to the negative 7 power coulombs, or about 100 nanocoulombs, which is very small, but I would say more accurate. And then as I pull it close together, say at about half an inch, which would be about 0.013 meters or 13 millimeters. We could use those, just knowing those values and Coulomb's constant, which never changes. We could actually calculate the force, in this case, the repulsive force between these two balloons. And I went ahead and did that, and just kind of showing you my work to see how this can happen. We have the force is equal to 8.99 times 10 to the 9th, the Coulomb's constant. And then assuming that the charge on the balloons is about 100 nanocoulombs. Here I converted it to coulombs because to conveniently be able to cross them out with Coulomb's constant. So 1 times 10 to the negative 7 coulombs for both balloons. And under there I put the meters, so it's 0.013 meters or 13 millimeters, and I squared that value. And as you can see, I already crossed out the meter squared and Coulomb squared to give me just newtons. And as you see there, the final value for the force between these two balloons is about 0.532 newtons, or 531.95 millinewtons, which I would say is roughly accurate, if we assume that that is the charge on the balloons. And so, as you can see, this has various applications. If you know the charges and you know the forces of that these two objects exert on each other, you could calculate that distance, at what distance this force would be active, or with any other variable that you're missing. Anyway, that's my video. I hope you learned something. Thank you for watching.